This is the second of two force videos that I'm going to be posting today. This one deals with friction and the normal force. Particularly, we'll have an extra normal force that we don't normally have to deal with in this problem. So, the setup is shown right here. We're pushing on two boxes. So we're pushing on box 1 with a force of 120 newtons. And box 1 is touching box 2. And they're going to slide across the floor, and we want to determine the acceleration of these two boxes. The coefficient of kinetic friction is given, and hopefully it's pretty clear that this is a forces problem and that we're going to need F equals ma. We're going to need a coordinate system sooner or later, so I will just choose one right away. We'll use our standard x is positive to the right, y is positive up coordinate system, and whenever we're dealing with forces, we want to keep track of the forces we have involved. And we'll do this with a free body diagram. So to begin with, I'm going to label some forces actually on my diagram up here. Each one of these boxes will have a force of weight. Weight 1 for box 1, and weight 2 for box 2. The push force is already shown. We'll just call it F push. Both boxes also have a normal force because they are in contact with the ground. I will call these Fn1 and Fn2 for the normal force on box 1 and the normal force on box 2. We also have friction acting on each box. Kinetic friction, Fk1 and Fk2. But these two boxes are also pushing on each other because the two boxes are in contact. And whenever we have contact, we get a normal force. So we'll have a force acting to the right, the normal force of box 1 pushing on box 2, and a force acting to the left on box 1, the force of box 2 pushing on box 1. So this isn't the most clear free body diagram in the world. There are an awful lot of forces going on. So let's make separate free body diagrams for each of our two boxes here. For box 1, we have the push force acting to the right, weight 1 acting down, Fn1 acting upward, the force of friction, Fk1, acting to the left, and the force of box 2 pushing on box 1, also acting to the left. So that's Fn2, 1. Fn1, 2 is the force of box 1 pushing on box 2. Which means that force is applied to the other box, so it doesn't show up in this free body diagram. Then, we will want a free body diagram for box 2 as well. So, again, we have a weight force acting down, weight 2, and a normal force acting up, Fn2. We have friction resisting our motion. The kinetic friction force, number 2, acts to the left. But we can't put the push force in this free body diagram because we're only pushing on box 1. It's box 1 that pushes on box 2, not our hand. So, we have a name for that force. The force of box 1 pushing on box 2. That's Fn1, 2. For the force of box 1 pushing on box 2. A couple helpful notes, or one helpful note to make here. Fn12 and Fn21 are a Newton's third law force pair, which means they have equal magnitudes and opposite directions. So hopefully you can see from the picture, the free body diagrams, that those forces point opposite directions. But it will be important later that Fn12 and Fn21 are the same exact force. So, now we need to start writing our F equals ma equations. I'm going to start with box 1. And we will eventually need a bunch of F equals ma equations. But to start with, hopefully you can see the acceleration is going to be in the x direction. The box is going to accelerate to the right. So, let's start off with our net force equation in the x direction. So, on the right side of this equation, all we have to do is decide, is the acceleration 0 or is the acceleration not 0? And here, the question asks us to determine the acceleration. So it's a pretty good assumption that we are going to have an acceleration here. So I'm going to leave this right side as equals ma. And I want to be specific because I have two masses, so I'm going to say equals m1a. Then I have to look at which forces I have in the x direction. And one of them is the push force in the positive x direction. And then I have friction force 1 acting in the negative x direction, and Fn21 also acting in the negative x direction. So now that I have my equation more or less set up, I can bust out any equations or components that I need. For this setup here, all of my vectors line up with x or y already, so I won't need any components. The push force, we know, but for now I will just call it F push. The kinetic friction, we have an equation for the kinetic friction. It's the coefficient of kinetic friction times the normal force. And we want the normal force caused by that contact surface, which is Fn1. Then we subtract Fn21. Nothing we can really do there. The normal force is a passive force. That's all we know. All equals m1a. So, to kind of take stock of where we're at, the acceleration is what we want. But as of right now, we don't know Fn21 or Fn1. So right now it seems like we have three unknowns. So I don't know about you, but I don't really want to solve a three-way system of equations. So let's see if we can't figure out one of these three values so that we can plug something in right now. We've tried the x direction, so let's give the y direction a go. Still from box 1. Net force in the y equals mass times acceleration in the y direction. And in the y direction, all we have is Fn1 acting upward, positive, and weight 1 acting downward, negative. And then on the right side, the acceleration in the y direction is 0, because our acceleration up here points to the right in the x direction. This means that Fn1 equals weight 1. And weight is equal to mass times gravity, so Fn1 is equal to m1g. So when we put this into our calculator, we get 5 kilograms times 9.8 meters per second squared. And we get a value for Fn1 equal to 49 newtons. So now we know at least one of these unknowns. So we know Fn1, and now we only have two unknowns. That's a much more reasonable value. So I'm going to rewrite this equation down here with the numbers that we know. 120 newtons is our push force, minus our coefficient of friction, 0.2, times our normal force, Fn1, 49 newtons, minus whatever Fn21 is, we don't know that yet, equals the mass, 5 kilograms, times our acceleration. I am going to box this equation in green because it has two unknowns and it will be helpful to us later. So even once we found Fn1, we still don't have enough information just from our box 1 equations to proceed. So I'm going to go and start looking at box 2. Maybe I can find enough equations to make a system of equations here. So again, starting in the x direction, because the acceleration will be in the x direction, we do expect an acceleration, m2a, is what the right side of that equation becomes. As a quick note, we do expect the same acceleration for both boxes because they're connected together. If you push box 1 5 meters, box 2 will also move 5 meters. And then we look at our free body diagram to see what forces we have in the x direction. And we have Fn12 acting in the positive x direction and Fk2 acting in the negative x direction. So, plugging in any formulas we might have, nothing for Fn12 minus the coefficient of kinetic friction times Fn2. Just like before, we want the normal force at the contact surface that's causing the friction. So we want Fn12 in this case. And that will equal m2a. So, just like before, it feels like we have three unknowns, Fn12, Fn2, and our acceleration. But if we go write our y direction equation, we can solve for one of these. On the right side, acceleration in the y direction is 0. And in the y direction, we have Fn2 acting upward, positive y, and weight 2 acting downward in the negative y direction. So, Fn2 equals weight 2. And weight 2 is just m2 times g, or 9 kilograms, times our 9.8 meters per second squared. And we get a value for Fn2, my apologies, of 88.2 newtons. So rather than having three unknowns up here, we now know Fn2, so we now have two unknowns. So plugging in some values here based on what we have, we still do not know Fn12, so I'll leave that as Fn12. Mu k is 0.2, normal force 2 is 88.2 newtons, and that will equal 9 kilograms, the mass, times whatever acceleration we have. So this equation also has two unknowns. And they are the same two unknowns that our other boxed green equation has. Which means two equations and two unknowns. Hopefully you're seeing a pattern here now. We will need to solve a system of equations. So, let's work this out. We want to solve one of our two equations for one of our two variables. I usually like to pick the simpler equation, and I think this equation up here is simpler. So, to rearrange this equation to solve for Fn12, good rule of thumb is solve for the variable you're not trying to find first. On the other side of this equation, we have our 9 kilograms times our acceleration plus 0.2 times 88.2, which is 17.6 newtons. Now we're ready to take our other equation and plug this value into it. So our other equation, we had 120 newtons, our push force, minus 0.2 times 4.9, so minus 9.8 newtons is our friction force number 1. Then we have minus Fn12, or minus Fn21, which is the same as Fn12. So minus, and put all of this in parentheses to be very careful, 9 kilograms times the acceleration plus 17.6 newtons, and all of that still equals 5 kilograms times A. So now we want to group like terms, so I'm going to distribute first 120 newtons minus 9.8 newtons minus 9 kilograms times A minus 17.6 newtons, because that negative over here distributes into both of these terms, equals 5 kilograms times A. Combining all the terms on the left side that are just numbers, so these three, gives us 92.6 newtons on the left. And combining all terms with an A in them on the right gives us 14 kilograms times our acceleration. So from here, we can just solve for our acceleration, and we end up with a positive 6.61 meters per second squared, because a newton divided by a kilogram is a meter per second squared. Because a newton is a kilogram meter per second squared, so you just cross off the kilograms. This is our answer. However, this isn't the only way we can do this problem. In this problem, we had two systems. We looked at box 1 as a system and looked at only the forces that act on box 1. Then we looked at box 2 as its own system and looked at only the forces acting on box 2. But there's another way to do this problem that I want to show you now. So kind of back to the beginning, get our coordinate system back up here. Let's look at both boxes at once as our system. So, if we want both boxes to be our system, then our free body diagram has to have every force that acts on either box. So, acting downward, we have weight 1, and we have weight 2. Acting upward, we have Fn1 and Fn2. The push force is still acting to the right, and friction still acts to the left. But now we've got two friction forces, Fk1 and Fk2. And that actually turns out to be it. So you might be wondering, what about Fn12 and Fn21? There's a couple of ways to think about this. One is that Fn12 and Fn21 are what are called internal forces, which means those forces come from two pieces of our system pushing on each other. So since both boxes are our system, any force of one box pushing on another is not included in our free body diagram. Or, another way to think about it is, well, Fn21 points to the right, and Fn12 points to the right. Sorry, Fn21 points left, Fn12 points right, and they have equal magnitudes. So these forces will cancel out anyway. So we could write them in our F equals ma equations but they're just going to take up space and clutter up our free body diagram. So I'm going to leave them off. So our acceleration is still in our x direction, so it makes sense to start with our x direction. So the right-hand side of this equation will be equal to ma, but I'm going to write the left side first. For our x forces, we have a push force in the x direction, positive x direction. And then in the negative x direction, we have Fk1 and Fk2. Then to figure out what we plug in for the mass, we need to remember that our system is both boxes. So we need the mass of our entire system. So we want the total mass of our system, mass 1 plus mass 2, times the acceleration. Now to bust out some formulas, the push force has no formula, it's just 120 newtons. But Fk1 is mu k, the coefficient of kinetic friction, times Fn1. And Fk2 is mu k times Fn2. And that all equals the total mass times the acceleration. So we know almost every value in this equation except Fn1 and Fn2 and our acceleration. So if we can find Fn1 and Fn2, we're good. So I'm going to do these in green. The only way to find Fn1 and Fn2 will be to go back to looking at just box 1 as our system. And remember, the free body diagram for box 1 had Fn1 pointing up, weight 1 pointing down, the push force acting to the right, kinetic friction 1 acting to the left, and Fn21 acting to the left. But this won't really bother us because all we want is the normal force, Fn1, and that's in the y direction. And the y direction is simple. There's no acceleration in the y direction, so we have equals 0 on the right. And then just like before, we have positive Fn1 pointing up the positive y direction, minus weight 1 equals 0. So solving for this, normal force 1 equals weight 1, which we already showed was just 49 newtons. So now we have Fn1, no longer an unknown. And we can go look at box 2 as well, because we still need Fn2. To remind you of that free body diagram, we had Fn2 acting upward, weight 2 acting downward, the force, the normal force of box 1 pushing on box 2 to the right, and the force of kinetic friction number 2 to the left. Again, we want the normal force, the one in the y direction, so we will write ourselves an F equals ma equation for the y direction for box 2, which looks similar to the equation for box 1. Normal force 2 in the positive y direction and weight 2 in the negative y direction add up to give us 0. And before, we already showed that the normal force 2 is equal to weight 2 equals 88.2 newtons. So now we have Fn2 as well. So back to our blue equation up here that we left off on. Now we have every variable we need to solve except the acceleration, and that's the one we're looking for. So the push force is 120 newtons minus the coefficient of friction, 0.2, times normal force 1, 49 newtons, minus, again, the same 0.2 for our coefficient of kinetic friction, this time times 88.2 newtons, which is normal force 2. And all of that equals the total mass, 14 kilograms, 5 kilograms plus 9 kilograms, times the acceleration. And if you grind through this equation again, it turns out on the left-hand side, you'll end up with that same 92.6 newtons equals 14 kilograms times A, and you will still end up with A equals 6.61 meters per second squared in the positive direction. Either of these two approaches will work. I think the systems of equation approach is maybe a little more intuitive because it's easier to think of each box on its own rather than thinking of both boxes together at once. Though you do need all four F equals ma equations to get your answers there. X and Y for both boxes 1 and 2. If you make both boxes your system, like we did here, you only end up needing to write 3 F equals ma equations. And 2 of them are pretty simple because they're y direction equations and our y acceleration is 0. But either way, you end up with the same acceleration at the end. I hope these problems have helped you guys and will aid you in studying for your test on Monday. And I will see you in class on Friday.